Good afternoon, everyone. I'm Hilton Sarias, and I'll be giving a brief definition of topology. Well, several other persons are already presented on it, but I'll be taking a different perspective. Topology, for us to have a topology, we need to have X, which is the arbitrary set, and we need to have a tau. And the axioms that we have three axioms: axiom 1, axiom 2, and axiom 3. The first one is X, and the empty set is the element of tau. Well, we already know this, so I'm just going to go through it quickly. Finite intersections of tau is also element of tau. Finite union of tau, also element of tau. Okay, what does this axiom really mean? How can it be applicable in reality? Let's look at sodium chloride. We all know about that. Salt. Everybody uses salt every day, well, except Rastafarians. Sodium, chlorine. They're both very dangerous to the body if you use them separately without being the compound salt. You could use salt, but you cannot drink sodium. You cannot drink chlorine. It will damage you. So how does topology apply to this? We said that X and the empty set. X is the arbitrary set, and the empty set must also be an element of tau. So we're going to try to define tau based on this, and we're going to also try to define X based on this. So X is the arbitrary set. Let X equal to the set NaCl. And our tau, we're going to let tau be elements, all elements on the periodic table. As long as it's a unique atom, it's an element. So we have all elements. Now, if you notice, when we combine these two, we do not maintain the properties. This now becomes edible. You can consume this without dying. These two, you can consume them and you will die. These are elements, this is a compound. So, looking at the first property, X is an element of tau. The empty set is also an element of tau. So this one is satisfied. Looking at the second property, intersection of union of tau. Is it an element of tau? Yes, because if you have separately union, let me give a geographical representation of union. Say for example we have two disks, and we have let's say we have, imagine these two disks out in the open, and we're passing wires through them from the roof to the wall. There's a point there, it goes through, comes down. Point there, goes through, comes down. There's a point that goes through here, comes down. Okay. Union. When we're looking at union, we're looking for all of these points. This point, this point, this point. So for the union, we're going to have 1, 2, 3 points, right? And each one of these points, if you look at this, they're actually the same thing because they're on the same wire. So we only have 3. Instead of 1, 2, 3, 4, you'll actually only have 3. So for the NaCl example, we'll only have Na and Cl. So that's our entire X, and that is part of tau. The empty set is by definition a part of any given set. So intersection, this is satisfied. For the last property,
union.
Yeah, union, thank you. Intersection. Intersection is this part, only this part that has both properties, this and this. That's sodium and chloride. And chlorine, we have NaCl. This here is the intersection. Is the intersection a part of tau? Is it an element? No, it's not an element, and it does not have the properties of the initial because it's poisonous. The first one were not poisonous. So this property is not satisfied. Hence, a topological space is not defined on that set. So this is not a topology.
Okay.